freaking busy music club has gotten. We have a meeting coming up, and I'm trying to rally all my officers together to start getting like the administrative session planned out.
Yeah.
And we have until the 25th. It's the 13th. That's a little more than a week.
Thank you.
Thank you. And my secretary is MIA.
Yeah, I need to rebuild Earth Club again. I lost my club, I think.
Yeah.
I still don't know what happened to Link. I haven't seen Link around.
No one that you've talked to wants to take it on?
Well, everybody else graduated.
Oh.
And I haven't like openly recruited yet, which I might do that today.
Yeah, you should do it.
I forgot about your writing assignment.
Don't look at me, I'm already busy enough. I would take it on if Chiharu hadn't snatched me up first.
Oh no.
I didn't even want to. I wanted to start my own club. Like, I wanted to start the pre-med club, and then...
Oh, you should totally do that.
Well, now I'm kind of invested in music club. It's become my baby. I brought it back from the ground up.
Yeah.
I spent 2 days on the bylaws, so...
I was supposed like talking with them about working at one in Denver, and then they were like, "Oh, let's just switch you to Vegas."
I think I want to do another demo.
What do you need?
No, it's fine. I'll grab it.
So what do you need? I'm right here.
Iron 3 chloride and potassium thioisocyanate in the dropper bottles.
Prussian blue.
No.
Ah.
If you're really into just like hanging out in your air conditioning,
You could if you wanted to. You have the stuff for it. I isolated it one time, but I couldn't separate it, and I was really sad because the particles are too fine.
what?
You think I've been there for 5.
A long time.
Just
yeah.
for this bachelor.
Yeah, it's thiocyanate, so.
Yeah.
Sodium thiocyanate.
Yeah, or I think we have potassium, but same thing.
Same difference.
Yeah.
Also, I printed this at home and my printer doesn't work super well, so it like kind of like
Oh, that's
messed
fine.
it all up.
Oh.
It's interesting. I didn't want to print it, and then I
Hi.
Hello? Mm-hmm. Point one's fine.
Regarding our next meeting.
Sweet, thanks. Bye.
They have a week to take care of all the items needed.
At least for now, yeah.
They're gonna jump up at us and next time.
I was like, did we have a class
Just secret class and you weren't invited.
Great. If somebody have this bulletin. You can like walk in if you're trying to give it to somebody.
Oh.
It's like somebody has a special delivery.
I'll see you later. Oh my god, yes.
Struggling with that, so like trying to prioritize that, but I ended up like not really doing that either. So
Been a lot.
Thank you.
yeah, I think you're I'll just do the reading questions.
Yeah.
I'll do it also.
Yeah, we can make them up this afternoon.
Okay, okay.
Grab the wrong thing.
You got it back.
It's a calcium isocyanate. Like it's right here. I just need the isocyanate. I'll put it back later. I'm just grabbing the entire chem closet.
There's only one class that I got this week. In person. Yeah.
How many demos are you squeezing in here?
Oh, well, they're fast, that's why. And some of them we may have seen. I don't remember.
Not gonna lie, I've probably seen all of
I mean,
them.
I passed this Spanish AP test.
I'm a very prolific chemistry YouTube watcher.
So,
I kind of want to.
Niall Reddy's might get done.
7? Okay.
He made his own liquid nitrogen containment and creation kind of
Oh, nice.
apparatus. It was
now
so cool.
you got me curious now, but
I just don't know how to like.
I mean, he converted diamonds into CO2, which he used to bubble into water to make sparkling water.
I was like looking on.
So,
It was like if you
Yeah,
have 400
it's-
more credits, then it's like.
it's funny.
But hey,
he has a lot of fun with what he does.
All right, are we all here? All right, happy Thursday. So I hope everybody enjoyed their Veterans Day. But yeah, so we're kind of a good week to reset here and play catch up. So that being said, so there's a few people that have missed like quizzes and other things. And so lab period today is a good time for makeup. So again, right, just a reminder, there's no official lab this week. So you get a day off if you have a Thursday lab. But we are conducting makeups today, and so many of you have emailed me, and so we have the setup ready to go. It's fine if you didn't email me, we can squeeze you in, grab whatever we need. But yeah, let's do makeups today in lab, and then also, like I said, quizzes. So if you're missing a quiz or anything, we can take it during lab and just get that out of the way. So catch up, and then double check your grades. There's a few no names, and then I'm behind on the grading. So I haven't graded like all your flame labs and on down. So don't panic if it's not in there, but from the Mendeleev on up, it should be. So if you're missing a lab, I have a few no names. So I would also come hound me during lab. Again, that's a good time to bother me. And again, right, if you need help, tutoring, lab today is another good time. Otherwise, right, make an appointment with me, see me in office hours before or after class. Right, I want to see you. That is literally my job. And right, again, so just make an appointment with me. That's the best thing to do. Other questions, comments? And so just so you can see on track what we're doing. So we're kind of skipping around. So we're going to leave the geometry behind, right? So again, the VSPR sheet is a really good thing to kind of put side by side when we're working with the Lewis dot structures. You're not going to be tested over geometry this quarter, right? We're going to save the official testing of that for next quarter. But again, you should be thinking in 3D all the time. So if you start thinking in 3D now, right, that'll just make the rest of your life easier. And then just kind of looking at where we're going. So we're in chapter 7 and 10. And so we'll kind of be finishing up these Lewis dot structures. So we're going to look at our polyatomic today, and then hopefully get to all these demo things that I have going on. So let's warm up then, unless there are questions. So see if you can do phosphate now. So think back to everything that we talked about last week, right? So how many electrons we're bringing to the party, trying to maximize our octet rule, and then trying to minimize formal charges, and seeing if you can remember what formal charges are. And then a hint, so we haven't looked at a charged species before, but previously our formal charges needed to equal to 0 since we were, again, dealing with neutral molecules. So in this case, we have a 3- charge, so we need our formal charges to add up to 3-. So go ahead and start on this. I'll give y'all a few minutes, try to sketch this out. Again, right, don't focus on like what's the right answer. Focus on the method. How do you get there? Is marked late or missing?
Missing.
Oh, look, because
I'll hunt for it. See if I still have it.
yeah, because it should be entered. So just double check. So you should be attempting to write something down. Kind of looking around, right? That's the whole point of this exercise. If you don't get it right, you're trying to figure out how to analyze the structure. All right, I'm seeing some decent looking structures. So let's kind of go through the thought process here. So first of all, how many electrons are in our party here? 32. So I hear 32, so let's see. So 5 from phosphorus. We have 4 oxygens, so 6 times 4 is 24. And then we need to account for this 3 minus here. So I didn't explicitly address this, but right when we have a 3 minus charge, we're saying we have 3 extra electrons. So I kind of put that like so as my bookkeeping. And if it was a positive charge, right, you would need to subtract electrons. And so yes, I agree with our 32 electron conclusion. So excellent, right? So that's the first key step, is you have to have the correct number of electrons, right? If you start dropping and adding electrons, then your structure is essentially meaningless. And so everything else, right, is just kind of detail and tells us about our structure. And so how did we approach this? Like I said, I saw a pretty decent amount of structures, but how do we get there? How do we start? So P in the middle, so that's usually a good guess. And kind of put our least electronegative element in the center. And then, right, we could even just start by drawing a line to all of them. And then I would fill in our electrons. And so we can do some quick math here. So this is 8, so 8 times 4 is 32. So I'm just going to fill in my electrons like this. Okay. And again, we're not saying anything's right or wrong at this point. We're just going through our process. And okay, electrons filled in. Now we need to put our formal charges in. So what's our formal charge on our phosphorus? And we can go through it together. All right, so remember formal charge. So it's valence electrons, so 5. And then how many bonds does it have? And then no other electrons. So we have a 1 plus formal charge. And then what's the formal charge on our oxygens? And so they're all symmetric. So we can pick one and then use them all. So what's our formal charge on oxygen? What did you say?
Should be -1.
So -1, right? So let's go through that process. So 6 minus 1, 2, 3, 4, 5, 6 minus 1 bond. So yes, -1 indeed. And then, okay, let's just double check a few things. So if we add up all our formal charges, so these cancel out, and then that leaves us with a -3 charge. So that's good, right? So now that's kind of looking good. Let's double check our octet rule. And so, okay, octet, right? They're all satisfied by the octet rule, including our phosphorus here. Now, I saw some people drawing other things. So what could you do, and what's kind of the hint that we need to maybe do something? Because there's something about this structure that tells us that we could make additional structures.
I'm not sure what you're asking.
Is it about the lone pairs that are on all the options?
I mean, they're there, but I saw, what I'm getting at is I saw a lot of double bonds, but how did you get to that conclusion?
I made a mistake and I had 5 bonds
Well, it's actually, so we haven't discussed that yet. Well, you're actually not wrong. So what you're getting at is this kind of rule of the expanded octet, right? And so why you would be tempted to maybe draw a double bond and why it's considered appropriate is, let's go back to our rule on minimizing formal charges, right? So we have next to each other a negative charge and a positive charge. So that's kind of telling us, let's try to get rid of this. And so we're going to do that. And again, right, you could have gotten here in a different conclusion. But I'm going to move one of my bonds over, one of my lone pairs, move it from a lone pair to a bonding. And now I'm going to draw this out. And so what we're also kind of getting at is we're trying to tease out what are called these resonance structures. But we'll see again, right, the power of it. And so now I'm just redrawing my structure here. And then, right, we want to do the same analysis of our formal charges. So now phosphorus, so 5 minus 1, 2, 3, 4, 5. So that's fine, right? Now it's 0. This got minimized to 0. And then these other oxygens, right, still have a -1 formal charge. All right. But then you did bring up the point, okay, well, now we did violate the octet rule. So not completely out of the question. And we just want to say, right, that phosphorus essentially feels 10 valence electrons. And so the idea behind this is, well, let's start off with the general statement. So usually there's like this general statement made, and it's always, let me pull up a periodic table instead of just staring at it. Are you serious? Sorry. Sometimes Google like tries to autocomplete and it was like trying to send me to a poker website. But I think that just like tells you that there's way too much online gambling. But anyways. So what the kind of general rule is people say, oh, okay, once you get to this third row, and well, I'll quote the misstatement and then we'll look at what is actually going on. And I have to say this because it's in textbooks, right? So they say, like, once you get to the third row, they can invoke d orbitals. And that is generally the explanation as to why they can do this expanded octet. So third row does expanded octet. But what we need to be clear of, there are absolutely no d orbitals involved. This is an extremely erroneous statement that is perpetuated by textbooks and many professionals. I'm not going to go into the derivation right now because I could totally prove to you why you do not need to invoke d orbitals and it actually doesn't make sense. So what's the argument then? Why can phosphorus do an expanded octet versus nitrogen? So then let's ask another question. Why does PF5 exist versus nitrogen pentafluoride? Well, the argument, again, goes back to our geometrical constraints, really, because if we kind of look at it, so now let me draw out our structure. So this is our phosphorus pentafluoride here, trigonal bipyramidal structure. Again, I don't want to get like super into it right now, but you can kind of see how this is in line with our p orbitals, right? If we go this way, this is also in line with px, py, so we can still do it. Like I said, I didn't want to get into the total derivation today. That's not the point. But then why doesn't NF5 exist? Well, it's simply that nitrogen is too small to accommodate all the fluorines around it, so hence why you do need to have a larger molecule, or atom, excuse me. So that's why this erroneous statement gets made, but it's not the true explanation. And so I think gas phase calculations show that if NF5 were to exist, that the two fluorines on the, so I would call this the Z axis, so Z means the principal rotation axis, so highest symmetry, but these would be elongated. And so basically, right, that's not a stable structure, And so that's why it can't hold itself together and it doesn't exist. You know, again, maybe you could get this to exist temporarily in the gas phase, but again, it'd be pretty unstable from those elongated bonds. All right, so again, back to your point, expanded octets are okay. And so we might see this, again, expanded octets. So it's okay if we have 10. We could even see 12. So let me just show an example. So sulfur hexafluoride, this is kind of our classic octahedral complex. And of course, so analyzing this structure, what's our total electron count on sulfur? How many does it feel? Right, and just kind of highlight, right? So count them up. So how many is it feeling there? So 12, exactly. And again, right, this is fine. A little unusual. So, right, it feels 12 valence electrons there. So again, hypervalent, but is fine. All right, so then back to our phosphate. Oh, sorry.
Sorry, this is kind of unrelated, but does the, like, do double and triple bonds, like, change the three-dimensional shape of the molecule?
So let's get into that, like, right now. So, like, that's a perfect question. And so if you remember from our chem compound thing, so let me pull this up. So if we look at what you're referring to, so no, the number of bonds, whether it's double, single, triple, right, that doesn't matter. So it doesn't matter how we've drawn it, right? So either way, it's attached to 4 substituents. So then we can still use that compound chem sheet. If I could freaking get it. There we go. Sorry. And so yes, we can do our same analysis. And that's why I say it's good to practice this now. We're just kind of setting us up for success in the future. I'm not trying to test y'all, but if you can see this, right, you'll be in great shape. And so to your point, so we're still doing 4 electron pairs in our phosphate, right? Again, it's attached to 1, 2, 3, 4 things, no lone pairs. So we can go to our 4 electron pair group here. And so what geometry do we expect this to be? Tetrahedral, right? So that's kind of the beauty of this sheet, is that it works for everything. And like honestly, so this sheet makes a weird disclaimer in my opinion. So it says fails for isoelectronic species and transition metal compounds. I don't actually find that that's the case. I find that this sheet works out pretty well for transition metals. So again, this is very helpful. So to your point, right, we're seeing it in 3D. We're seeing that it's tetrahedral. Now let's address the other points about this double bond and what we're really trying to say with our Lewis dot structures. So it doesn't matter, right, what bond I choose to pick, but we have to think about what this is saying, because what we're trying to give is like our true electronic nature of this phosphate, right? And so what I mean by that is, well, let's draw more resonance structures. And so we're drawing these resonance structures to really show, right, again, the averaging of these electrons. And we're thinking about everything as a probability density map as well. And so really what we're saying is, right, we're distributing this double bond around these 4 bonds kind of evenly. And you could get, right, your bond kind of order average. So I'm just trying to draw every single permutation. So this would be, right, a complete answer here for an exam, right? If it said list all resonance structures, you want to draw out every single resonance structure. And so then, right, we can calculate roughly our bond average. And again, this is just kind of giving us a feel of how strong these phosphorus oxygen bonds are. So we have 1, 2, 3, 4, 5 bonds, right, divided by 4 atoms, so we have about, right, 1.25 bonds roughly. So what is this telling us? Okay, we're saying we have a bond that's slightly stronger than a single bond, right? But it's not pure double all the way around, so it's not as short. So it's kind of somewhere between in the realm of strength, right? And again, we're not saying that this bond is rotating around. We're saying this is how it exists, right? And it's an average of all these structures, including this one, right? So this is also a relevant structure since it satisfies the octet rule, right? We're trying to describe basically our quantum mechanics and our probability density maps and kind of simplify them, right, into these Lewis dot structures. So obviously it's not going to track perfectly, but it is still really powerful. And again, right, it's giving us this sense of how it behaves. And again, other key points. Our oxygen has a -1 charge, so that's telling us, right, how it dissolves in solution. And again, that our cations are going to be attracted to this part. So that's telling us, right, how the phosphate is going to dissolve and why it dissolves into our polar water. So all those things kind of come into play. All right, so does that make sense? So again, a complete answer is all of these resonance structures kind of averaged with our correct number of electrons, and then you want to put your formal charges, right, anywhere that they are appropriate. Yeah.
Is there a hybrid way to write that too?
What do you mean, like a hybrid way?
Is there a way to show that that double bond is moving between all three of them?
Just kind of like that. I mean, other ways that you might see it represented is, you know, something like that, where they kind of draw these like partial bonds.
Right.
But like sometimes if you see it like that, you're not quite clear, like how many partial bonds is this? So, yeah. But people may use like a variety of structures to kind of try to show the same thing, to your point. All right, so I'm going to try to keep it moving since we have a lot to cover. And then you should have gotten the polyatomic sheet, so I don't expect y'all to memorize anything, but you should just start familiarizing yourself with these. Obviously, we're going to see a lot of hydroxides, maybe see thiocyanate. Acetate is one that always confuses students because it's written in 2 different forms. And then you might also want to visualize acetate as to, right, what it is. So this is, right, acetate, so the ion, and it comes from acetic acid. So this is just vinegar, but we'll get to more of that in a second, but I just want to see that this often confuses students in lab. And then just watch the spelling, right? You have nitrite for 2 oxygens, nitrate for 3, and we see that kind of repeated. I think that's further in the lecture notes. All right, so let's start looking at some of these reactions. So chapter 10 is kind of like a bunch of fun facts. I like to think of it as just like, here's a bunch of typical reactions, here's kind of the typical reactivities, and so we'll kind of look at that. And so the first kind of common reaction, and again, right, this is a reaction type, so this is called a synthesis reaction or a combination. And this is anytime, right, we have just 2 elements, so A plus B, and they come together to make one product, right? So we should have fewer products than we did reactants. And so some typical reactions would be like carbon plus oxygen, so just a pure combustion, rusting. So, right, that's iron plus oxygen gives us iron oxide. Same thing, so sodium oxide. Another one that we did do, so right, we did back in the beginning our hydrogen and oxygen balloon demo. So that, right, reacted to give us water. So that's another combination reaction. One that I didn't bring, but is another common one. I wanted to do it, but note to self, I think I need to keep a Bunsen, one of those like little, the lighters, you know, but the butane torch ones. I need to keep one of those on hand. Otherwise, I would have done this, right? So magnesium plus oxygen. If you've never seen this, we should just do it in lab. But right, you put those two together, the magnesium lights up super brightly, and again, they combine to make magnesium oxide then. Other things, so we should get into the habit of also practicing writing out our states. So again, right, this tells us how it reacts. So solid magnesium plus obviously oxygen's a gas, and then that gives us magnesium oxide solid. All right, so let's look at these ions in solution. So again, some of the similar concepts, and some of this is I wanted to do demos from other weeks. And so first of all, let's appreciate the difference between an ion, right, and a molecule. So let's look at ions versus molecules in solution. And so let's recap a couple of things that we talked about. And so first of all, so I'm going to have salt here. Just going to pour out some salt. All right, and then, so we're going to use, so this is a conductivity probe. And this is really nice, actually. I have a much greater appreciation of this now. So you can purchase this, right? You can see what it is. Actually, used to use a jerry-rig one back in the day before coming to this institution. So that's why I'm saying it's great that we have safe ones. And so, right, literally you can see how the circuit is broken. So then we need to complete the circuit. So some safety measures. I haven't plugged it in yet. I don't know if that was obvious. And so when you plug it in, right, I would not want to do that. That would be completing the circuit. And I've done that before accidentally, and it hurts. What you would never want to do, though, is complete the circuit with your body across your heart, right? So when working with electricity, kind of an easy safety tip is just use one hand, because again, right, you don't want to complete the circuit, and then it goes across your heart, so that would be bad. Safety first. So again, I'm going to hook this up. And so the point that we want to prove, first of all, so like I said, we have salt in here. And I think we made some statement with ionic compounds that, right, that the salt itself does not conduct electricity. So let's, okay. And, right, so all we're seeing is there's no movement of ions, right? So they're literally not moving. So there's no way for our circuit to be complete. So now let's test this with sugar. So, I mean, I guess we could stick this in for good measure. Oh, I forgot my demo cam. Okay, functioning. So, right, again, we stick it in the sugar, nothing happens. All right, let's compare a solution. So, sugar. So let's dissolve our sugar in water. And sorry, I need a producer. There we go. Let's see if that kind of works. So you can see my video. Hindsight, this is a little short, but sorry. Moving my cart over. So again, now we're going to dip it into our sugar water. So nothing happens. And right, again, that's what we expect. Let's maybe pull up, oops, I don't destroy everything. Let's pull up a picture of sucrose. And we could look at, right, any of those sugars, so sucrose, fructose, all similar, right? So again, it's a molecule. So discrete, go away. One discrete structure. Oh, sorry to interrupt, you're interrupting. Right, so again, right, we're seeing that there's no way for it to create ions in solution. So now let's compare that to our salt here. Here we go. I knew I had a Sharpie. Always need to label stuff. Again, safety first. And now let's try our pickling salt. So this is just a prepared 20% solution of sodium chloride. And oh, ta-da! Something finally happened. Right, so now we did complete the circuit. So let me show our video. So yes, right, so now we have ions floating in solution. And so that movement, again, allows us to complete the circuit there. Let me plug that for a second. And so going back to our lecture, so again, that's what this is just re-emphasizing. And so it doesn't matter whether we're looking at sodium chloride, right, or whether we're looking at a polyatomic ion like sulfate or anything else, right? There's tons of combinations of anions or cations and anions, right? So plenty of different combinations, but same concept. So again, our hydrogens are orienting themselves around the negative part, so that would be our oxygens of sulfate. So oxyanions, so this is just giving us a general trend. So like you're saying, most of your polyatomics have oxygen in them. That makes sense, right? Oxygen's very abundant. It also reacts with a lot of things. So oxygen also makes a thermodynamic sink. So that's why you find that. And again, refer to your polyatomics, but we're just looking at this general naming trend of more oxygens is 8, less is 8. And then we have other variations as well. So hypo meaning less, right? So now if we are kind of missing an oxygen from our ite in comparison, it's hypochlorite. Or if we have kind of more, then we have this per, so like perchlorate or perbromate. And again, you see that repeated there. So then to name it, it's pretty straightforward. So then you just name your cation and your anion. So that would be like sodium nitrate. If we had, so let's say we had this compound, so Fe3NO3. So again, same thing. We just want to identify in this case the oxidation state of our metal. So what's our oxidation state of iron in this case? Okay, double check. Oh, I might have messed that up. Sorry. Let's do something else. This makes more sense. Sorry.
+3?
Yeah, so +3. So iron 3, and then we just name our ending nitrate there. So straightforward with naming. And then, oh, I should mention, because there was a small typo in, I think, the naming. I think it had thallium listed as titanium accidentally. Y'all check the week's homework. We'll just double check that, because it's a minor thing. So I think it's thallium that was on the homework. But I'm pretty sure the answer key accidentally said titanium. But then you also did have titanium. But.
I think it was a TI, but it said thallium. That's the.
Oh, I remembered it the wrong way.
Yeah.
Either way.
Number 6.
Yeah.
I was like, I'm assuming it's supposed to be thallium.
Yeah.
Makes more sense.
And then with that, because it's also confusing, because that being said, right, titanium 3 plus is the common ion. So for our naming purposes, if it was titanium, right, you should name it like titanium chloride versus like titanium 3 chloride, for instance. But
So I noticed that our table that we got, like, my titanium only has a +4. So there should be a +3 underneath it, that is just more common.
no, I think I misspoke. No, I guess it's fine. I was just
For
trying.
like naming, if there's more than one, then we have to put the Roman numeral on it.
Yeah, that's the pesky thing about metals is they like to misbehave. So yeah, it's probably best to put the oxidation state in the Roman numeral if you are unsure.
Okay.
Because I'm probably like not gonna penalize you for
But
like
the
putting the
other
oxidation.
is not, right? There's just one.
Yeah,
Call it
well.
multiple times, right? Except there's exceptions.
I know, I don't want to say
Okay.
no and then that
Okay.
you'll find the exception, but yeah, metal naming is,
I'm just gonna put the Roman numeral.
yeah, that's best. All right, let's keep looking at other reactions. So let's see if we can get this to react. So then let's look at, well, actually, let's look at a few things. So we have metal oxides reacting with water, but before we jump to the oxides, let's look at our other reactivity here. And so let's just test out. So before we jump to calcium oxide, because these oxide reactions, so again, we have this general trend of these metal oxides react with water. But if you recall, right, we can also have our group 1 just metals react with water. So like sodium plus water, right, gives us sodium hydroxide and hydrogen gas. And then we have similar reactivity with calcium. So let's just compare. So let's look at calcium and water for a second. Again, I'll make calcium hydroxide because I've been neglectful in doing some of these demos, but well, there's a reason why I haven't done the sodium one. That is not ideal. Seriously? Okay, now I'll never be able to unscrew that. So let's start with calcium. Oh, that's lithium. Oh, did I forget calcium? I totally meant. No, metal calcium.
Metal.
Yeah, I thought I'd grab the tin, but I grabbed lithium instead. So we can do lithium while it's here. So let's do.
Tactical tweezers.
Alright, so I lied. So yeah, let's do lithium. Let me get our demo cam back up. It's functioning. Okay, good. So I'm just going to add some water. Get it a little closer. Again, I totally need a producer here. All right, so let's get out our lithium. So lithium is harder to cut than like potassium, I believe. All right, I actually don't want to do it in this test tube. Pickling salt. Let's do it in a beaker. The reason why I switched is because I don't want to create too much headspace and gas, so I'm trying to like calculate how much gas is going to potentially be involved. All right. And you can't see that. There we go. All right, so let's look at lithium. So again, this is going to be pretty mild. And hopefully the odor of hydrogen will not be too offensive. And so again, pretty unexciting for the most part is evolving hydrogen gas. All right, so that was lithium. So fairly quick, but again, that's just our metal reacting with water. So I'm going to do lithium plus H2O. Okay. Now let's try metal oxides. So the thing about these metal oxides is they're a little slow. But let's see. There we go. So I have here a little bit of magnesium oxide. Realize I don't have a spatula. We'll improvise. So let's see. So far that's not really doing too much. And so that's the problem with these metal oxide reactions is that they're kind of slow. And like I've added it and not much has happened. So just kind of sitting there. So eventually, though, we do expect it to do something similar. So again, right, these oxides eventually react with water to make hydroxides. And so that's something that we could do is kind of monitor the pH of this. But it also doesn't react very vigorously. So that's kind of the thing about these oxide reactions.
So, are all hydroxide solutions basic?
Yeah, so if I were to get some phenolphthalein, even with this, so right, that might have been a good thing to do with this is put some phenolphthalein and kind of see how it gets more basic over time. But yeah, that's something that I do with this lithium one, is we could grab phenolphthalein. Like I said, I'm missing the entire chem closet still.
So is lithium more reactive because it's an alkali metal?
Compared to what?
Compared to the magnesium?
Yeah, and so Brooke, I think, went to grab calcium because I wanted to show you all the difference between like the lithium and the calcium to your point. So right, it all goes back to the same things that we've been talking about. Sorry, I was trying to find our periodic table, right? So we could characterize it by the ionization energy, right? That has to do with it. Right, so ionization energy increases, so it's more favorable, right, for the lithium, so that's why it's super reactive. And then, like we said, so the reason why I didn't bring sodium and potassium is just because I want to do them in lab for safety reasons. Sodium can get pretty violent. I've done sodium a bazillion times, and every time it like can take you by surprise. And that's like, you have to respect the sodium. Like, especially if you end up with two pieces together and then they meet, that thing can like totally explode. Like, you know, the last time I did it in lab, even like down the hall, I accidentally like hit the ceiling with the piece of sodium. So don't tell anybody. No. But I will do it in lab for y'all another time. All right, so what else? So good. So let me add that. So right, again, we would probably want an indicator. So I didn't grab everything from lab, but yeah, then right, just thinking of how we can tell whether a reaction occurred. So you could again monitor your pH. And so a lot of these are kind of slow with the magnesium one that we were looking at. So magnesium oxide plus H2O, again, does the same thing, makes magnesium hydroxide. Is that calcium? Thank you so much. Let's see how this goes. Brooke, you're going to hate me. Let's look at it. Let's look at it. It's a lesson. It's a lesson here. All right. So pour more calcium. Wait.
More?
Yeah. Wait. Don't. Just sit tight for a second. Right. So let's look at what's kind of wrong with this calcium, and then we'll see how it reacts. And then you can get actual good stuff. This is good lessons though in chemistry. Right? So that's the whole problem with chemistry, is that chemistry is a practical science. Oh. Sorry, my mouse is wigging out for a second. Are we still there? Okay. So do we see this? What's wrong with that? What should calcium look like?
Oh, blurry.
What?
Sorry.
It's brown though, right? Is this the color?
It is brown, but what should calcium be? What do we know? No, I'm trying to find something with not text. But that's calcium carbonate you're thinking of. What about calcium? Is there something without, like, what'd you say?
Shiny.
Shiny. So the problem, and why chemistry, why you have to have experience with it, it's not shiny. So,
Tell them to call that next time.
well, we have a whole bunch of new stuff. So this is the old stuff.
Buried in that bin, so I have to dig it out.
Well, it should just be like the stock jar. Well, anyways, let's see how this reacts, because this is mainly copper oxide. And it's going to sit there and look at us. Are you sure? Do you want me to find the calcium?
No, I'm gonna go get it myself because I know exactly where it's at. I'm not gonna listen to them anymore.
So is that just really oxidized on the surface layer?
Exactly, right? So really oxidized. So that's something to just be like aware of, right? And like think about. So you're a chemist, right? You're in lab. So that's the first thing you're thinking about. Like before you even start mixing stuff together, are my reagents even good? And so especially with these group 1, group 2, right, those are going to go bad since, like we're saying, they tend to react with the oxygen. And so
Can it be, could you like physically disturb the calcium? Is it soft enough that you could cut it and then have access to the actual calcium?
Yeah, potentially. These are pretty small, so I don't know like how much salvaging we could do. But that's like the right idea for like, especially a block of potassium. I've, done that before. You kind of cut off all the sides or sodium, get off all the oxides, and then you're kind of left with a shiny surface. So yeah, so this is barely bubbling, right? Again, it's not giving us the appropriate reaction since it's mainly copper oxide at this point. And like I said, those copper oxides react really slowly in water. So they're not flashy like you might want. All right, so let's keep looking at other stuff. So this is kind of a preview. And so let's look at this acid. And so a couple of things about acids. And so the key word, some of the key words that we're looking at, let's back up a little, is, so let's look at hydrochloric acid for a second. And so hydrochloric acid, we're going to find, as again we continue our chemical journey. So this is called a strong acid. And so this term doesn't have anything to do with how much it hurts you when you touch it, but rather whether it fully disassociates or not. And so hydrochloric acid fully disassociates in solution, and that's all to say that it makes these two species. And even this is kind of an oversimplification. Again, we'll hit up acids and bases another time, kind of more formally. But what we also want to appreciate is what is actually happening. So let's draw out what actually happens. And so part of what you often read is, so H plus doesn't really exist. And so that just means that you just can't have like a tiny naked proton, right? So what actually happens, and so now let's back up with our HCl. And so basically instantaneously, when it's in water, so we have our water here. And water, again, is super special. So later we'll get into all these things, but basically we want to know that it's amphoteric, which means it can be an acid or a base. Oops. And so then in this case it's functioning as a base since it's going to pick up this hydrogen. And so movement of electrons, so you always want to start with the electrons. Right? I never want to see a little hydrogen jumping over like that. That is absolutely wrong. That being said, you will see online resources that may show that. And that is, again, inappropriate. Your OChem professor will lose their mind. And so then it would go over here. And so now we have our four. Well, there should be a ton of it. But yeah, this looks better.
Yeah, because it's buried under the chlorine monster.
And so then we get, right, our hydronium species. And so this is really what is going on in solution. Hydronium. And then, right, we would also make our chloride. So that's what's going on in solution. And so this is just kind of showing that process, again, how you don't have this hydrogen existing, but rather it binds with our water to make hydronium. Again, right, has our formal charge here, so that looks good. And then we can do a slight intro to organic acids here. So organic acids all have this key structure, so I wrote it out right with the acetic acid. And so why this is acidic is we have to appreciate this, what's called acidic proton. And so all this means with our acidic proton here is that this is the one that comes on and off when we are donating a hydrogen for an acid species. And so again, right, we have this equilibrium. And then once again, just recognize this would be your acetate, or more generally, so we should call it carboxylate, if I could spell. And this is our carboxylic acid group. And so why, again, this is so stable. And this, again, I think addresses other questions that have happened, is so we can draw a resonance structure for this. So I'm going to again, show the movement of electrons. So I'm going to move them. Again, you always want to move your electrons in pairs, unless you have a weird radical, but again, we're not looking at radicals right now. So generally, you always move them in pairs. So I'm going to make now a double bond. And then, so we can't have pentavalent carbon, or sometimes called Texas carbon. So that doesn't exist. And that means that those electrons get kicked up to oxygen. My double-headed arrow shows resonance. So this is, again, just showing electron movement. And so now I can draw my resonance structure like so. Again, I'll add my formal charge, right? And so what are we saying? And so what we're saying is that this negative charge is stabilized across this whole carboxylic acid group here. And so sometimes you often see this abbreviated like so, with these little dashes, right, to show that we have this double bond resonance. And then they'll put this negative charge kind of across here, again, showing that this negative charge is distributed right among both of these oxygens. And so again, that's what makes it stable, right? That we have this resonance stabilization, so that's why this is our acidic proton, and it's able to come off. All right, so let's look at a few other things. So now, if you look at this arrow here, so this is on purpose, so it's a double-headed equilibrium arrow, and these organic acids tend to be weak acids. Again, we're not talking about how strong or how much it hurts, but rather how much it disassociates. So now let's appreciate that with our lamp. And I hope I brought enough beakers. Questioning that. Okay. So I have hydrochloric acid. Now let me label this. And then we're going to compare it to our acetic acid. I wonder if I can dump this sulfate.
I'd be super impressed if you could. So it has a little lip, right? So, or a little force out.
Yeah, I'm like only semi-failing. Oops, that was an epic failure. Oops. Okay, now I'm giving up on my...
Don't do that. We need you.
Okay, there we go. Sorry, I knew I didn't bring enough beakers.
We only spilled half of it in the basin.
All right, so let's pour out hydrochloric acid. And so I attempted to get similar molarities so that, again, you can appreciate the effect. And let me label my beakers. So HCl. So I'm just trying to get enough HCl to dip in my little circuit. All right, so HCl, and then let's pour in our acetic acid. And I think the acetic acid is technically a greater molarity. All right, so let me plug my lamp back in. Again, safety first. Actually, I wanted a paper towel. Let me grab. Okay. All right, demo cam back up. Army's still alive. Okay, perfect. So let's start with our HCl. So again, strong acid, right? Fully disassociated. Let's see that. So nice and bright. So again, it's only 2 molar. So that's what's limiting us here. And then let's compare that to the acetic acid. Just going to rinse it off mildly. Just water. And now acetic acid. So let's compare. And so that's right, a little dimmer. And so the secret is, though, too, is I think this is supposed to be double the molarity. So I think it's closer to like a 3.4 molarity. And so let's do that again. So again, the acetic acid is weaker, right? Because there are less ions in solution. You have an equilibrium. Versus, again, see how much brighter that light is? It's kind of hard to tell on the camera, but again, right here's our HCl. So very bright, fully disassociated. There's 2 molar ions in solution. And then let's just see it one more time. So again, our acetic acid, weak acid, not fully disassociated, right? So you can literally see how, yes, you have less ions in solution because my light bulb is dimmer. Does that make sense? All right, let's take a little break. I think we're at our break point. So maybe, can we be back at like 10-ish, just because got a lot going on. But yeah, just try to take a quick break, run to the bathroom, and be back in like 5-10 minutes roughly.
Ow. Hi.
Oh yeah.
So I was watching a video last night, it was a Now Red video, and he said that it's a bad idea to mix solvents and acids, but he didn't really elaborate as to why.
Bombs, yeah.
Bomb.
I mean, it also
Bomb.
depends like which acids. Like it's usually nitric that's always a problem.
Yeah.
Yeah.
I had a nickel for every time I accidentally asked you to make explosives. I have 2 nickels.
But I gave you that paper on how to actually make explosives since you weren't curious. But yeah, I always forget about like that it needs sulfuric acid or some sort of like catalytic acid.
Yeah.
Yeah, it's not super easy to just nitrogenate everything.
Yeah. Probably for the better though.
You're gonna get somebody put on a list. I swear to God.
Oh, proton. Okay. Hello.
I wasn't going to be able to be in class. I have an appointment. I just wanted to check in. Are we doing a quiz today?
No, I'm not going to do a quiz today.
Sounds good. Thank you.
Ah, the sweet smell of acetic acid.
Yeah, I actually hate this acetic acid because I have a horror story from it though.
I hate the smell of hydrochloric acid, but I mean, it's generally an offense upon the senses.
Well, one time I used to work in a PChem lab. And we were doing oriented molecule experiments and using acetic acid. So they had a lecture bottle of, concentrated like 12 molar acetic acid stuff.
Right.
And I guess it ate through its bottle at some point, because next thing you know, there was 12 molar acetic acid shooting across the lab. So now there's like a puddle of 12 molar acetic acid in the middle of the floor.
That's
Yeah.
awful.
Yeah, we called for hazmat and then had to evacuate because it was horribly smelling, and we had to neutralize all that acid, and it was terrible. And I really do not like the scent ever since then.
I was working in my home lab, and I accidentally I poured some hydrochloric acid on the concrete floor, and
Oh
I
my
got
gosh.
to see concrete etching for the first
Nice.
time.
Yeah, concrete has a lot of calcium and
That it
stuff.
does. Yeah. I left a crater in my porch.
But it's big.
My grandparents were not happy about it.
Yeah, I mean, most people aren't happy with chemical unit, but I'm also convinced most people are chemphobes or whatever.
It's fun. It's fascinating.
It's life.
Right. because they
gonna
make
kill
it,
me
like,
later.
really concentrated acid too. Scarily concentrated acid. Cool chemicals. They work great.
I'm not denying that.
I want to get my hands on some sulfuric. So far I've been having a terrible time trying to find it.
Trying to think how to get sulfuric.
Drain cleaner. It's not pure, but it'll work.
Here, I'm gonna get phenolphthalein. I think it did. Now I forgot what.
I would never survive.
It's somewhere in there. I gave my. Do you remember the ionization energy pages? You had it. You said it like the other day in class.
Well, I was on it at that time. I can probably find it.
I got a copy of that page.
Let me see if I can remember it.
Go to the glossary. That'll help you.
Like, I know there's one of the, like, some of them, but not for everything.
Did you get your lab done? Did you get your lab done? I didn't finish my lab yet. I'm still working on my abstract.
I didn't turn it in because I wanted to no, a couple test labs. So most of my questions.
I'm trying to find this.
I'm listening, I swear.
Oh, that was it.
I was gonna be looking about the
Fair enough.
I just want to see all of them on one tray.
Am I available on the 29th?
Yeah, I didn't have time to get through it, but thankfully.
Yeah, I skipped over one too,
Once I work.
and I came back
I
for
don't
like
want to
5
spend
minutes
like 3
and
hours.
rushed it out.
Stagnant, yeah.
No, I left right when the time I basically, I turned it in. I turned it in.
What time?
Oh, hello.
I told you.
I was still, because I was still on the big problem.
How goes it?
Like,
Lab today?
I know.
There's no lab done. Today's the makeup day, so if you didn't get anything done, which I highly doubt.
Yeah, right.
All right, did we all make
You
it
could
back?
you could never get anything done right. Never.
All right, I'm going to try to check in on some of our reactions to see how they're doing. So I did grab some phenolphthalein so that we could, again, monitor our reaction progress here. So out of curiosity, let's just see what's going on. So this is our calcium, well, we'll call it calcium oxide. So I put some phenolphthalein in there. So the cloudiness is just from the immiscibility. So if you notice, right, your phenolphthalein is dissolved in ethanol. So just a little bit of ethanol, right, to get that organic compound dissolved. So that's not really doing much. Let's check out our magnesium oxide one. Ah, yay! So that's at least, so that was our magnesium oxide from earlier. So remember how it was just kind of sitting there looking at us? Well, it was reacting again, right? It's not explosive or exciting. It just kind of dissolves and then makes our basic solution. So again, it was a good thing that we got the indicator, because now we can clearly see that we're making hydroxide, right? Because otherwise, it's not really that evident. And then let's just check on our lithium. Again, this should be pink, yes, right? That's just what we expected. And then let's catch up here. So let's look at our calcium. So we did retrieve another calcium piece. And so again, before you start mixing your chemicals together, always check your purity. So I can't emphasize that enough, especially right, you go on to grad school, you want to do a big shiny new reaction, you got to make sure all your reagents are pure. Best advice I can give. All right, so now we have shiny calcium. Let's see if we can see that. I should have acquired a white piece of paper, but I didn't. So again, let's see if you can see that. If you want to come up and look at the bottle, right, feel free. So again, all we're showing is calcium should truly be a metal, right? And let's see how this reacts. Sorry, my camera's just a little slow. And so, yay, that does vigorous reacting. Don't bubble out, don't bubble out. Secondary container. So yeah, I made a lot of hydrogen gas, obviously. And then we can tell our calcium hydroxide, right, is coming out of solution. And then obviously more hydrogen gas is also being evolved there. Oh, and it's nice and exothermic. I'll let that finish thinking about its life in there. All right, let's keep looking at our reactions. All right, so we covered our acids. And so then, you should be familiar with how to name them. Again, I'm not really testing like explicitly on naming, but we have hydrochloric acid and then sulfuric. And so unfortunately, like the naming also isn't always like obvious since it's from like sulfate here. And then notice, so sulfuric acid is used a lot in like batteries, fertilizers, explosives, and then same thing, so nitric acid, so HNO3. We used that last week, remember, to dissolve the copper. So nitric acid is pretty nasty stuff. And so again, use a lot in explosives. And like I've kind of hinted at, a lot of these nitration products can eventually be explosive. And then we looked at acetic acid, and so again, some of you may be familiar with that in like food preservation, or you know, maybe like wine or something. There's also acetic acid in there. So citric acid, eventually we'll do a titration with citric acid, I believe. And notice this would be a triprotic acid. So again, we'll cover acids formally later, but just kind of giving us a preview. So it has 3 acidic protons is what that means there. And actually, let's look up citric acid. So citric acid is, of course, from citrus fruits. So it's our organic acid. You can also buy like citric acid, so it's used a lot in like candy making. If you've ever had those Zots candy, they have like citric acid and other like malic acid, I believe. And so this is our structure of citric acid. And what you should do is when you look at this is, okay, if it has 3 acidic protons, right, kind of find them out. So there's our 1 carboxylic acid group, right, with our acidic proton. There's our second one with our acidic proton. And third one with the acidic proton, right? So you can kind of see that structure, and again, the protons. And then we have carbonic acid, and so this is due to dissolving, right, CO2 and water, so that makes, right, carbonic acid. But there's also equilibrium processes, so we'll get into that later. HF. So HF is used a lot for like making chips and such. Also, again, like dangerous since HF, I don't work with it personally. That's kind of on my list of things I don't want to work with. And that being said, I have very few things on that list. But the problem with HF is what people say is like it doesn't necessarily like hurt when you get it on you. But then the danger is that HF reacts with the calcium in your bones. So obviously you don't want to have calcium liberated in your bloodstream and then having the potential to solidify somewhere else. And especially, right, depending where it re-solidifies, that can cause all sorts of problems, right? Like in your brain, it causes a stroke. So if you're ever working with HF, you need to have the calcium kind of antidote on hand, again, just in case you were to ever get it on you. So it reacts with the calcium antidote as opposed to you. And then phosphoric acid, so again, commonly used, again, fertilizer. It's an important biological buffer, but you also see it used as like a catalyst. It's also used in beverage preservation there. So you'll find it in your soda. And brief, again, overview, acids tend to taste sour. You probably know that from eating like vinegar or lemon juice. And then they neutralize bases. We've seen them react with metals. Oh, let's do that. So again, in terms of reactions, so looking at our activity series, and again, kind of appreciating our different reactions. So now I just want to demonstrate our magnesium, if I could find it. There it is. And again, just a quick reminder of magnesium's reactivity. A slightly bigger piece. So again, magnesium, let's get my cam out. So magnesium, oh, that's nice and shiny. And so I'm going to, before I drop that in there, where's my acid? There's my acid. So I'll put in some 3 molar hydrochloric acid because I want it to react on a regular time scale. And so again, let's just reminding ourselves of the reactivity. So again, right, acids react with metal to produce our hydrogen gas there. And then, like I said, we'll get into acids and bases later, but kind of in general, bases are slippery and taste bitter. So usually, right, like you can tell if something is bad because it has that alkaline product. Actually, so you know, like potatoes, right? Like if something is alkaline, that usually tells you that it's toxic. So I don't know if you know, like potatoes, like if they get green, they start making like bad alkaline or alkaloid complexes. And so that happened to me the other day because I attempted to eat potatoes that had sprouted too much, and after I cooked them, I tasted that they were still bitter. So again, from those alkaloids. So.
Did you eat them anyways?
No, I resorted to instant mashed potatoes. But yeah, so right, listen to your body though. Like that's why you have those receptors in your taste bud, right? It's telling you this is poison, don't eat it, right? So bases, that being said, tend to be poisonous. So right, you don't go around eating a bunch of bases. And then they produce hydroxide ions. All right, let's look at other reactions. So decomposition reactions. So this is when you have kind of one product that goes to, or excuse me, one reactant that goes to many products. And unfortunately, the decomposition of calcium carbonate occurs at like, I don't know, roughly like 900 degrees Celsius or so. I think it would work with a Bunsen burner, but like I said, I don't have a Bunsen burner in here. Otherwise, I would try to decompose it for you. Other good ones are hydrogen peroxide. See, I could have brought that one. And if we put it with a catalyst, right, potassium iodide, so that will break it down to water and oxygen. So that's another example of a decomposition reaction. Let's keep moving. So hydrates. This is just how to name them. So we have our common hydrate prefixes, so hemi, mono, di, tri. And so what's important to recognize is, right, that they're complex to it and they look a certain way. So nickel 2 chloride, for instance, so the hexahydrate is this very distinct green color. And then you would want to reference a purification book to figure out, like, let's say if you wanted to go from the hydrate to the anhydrous, there's different ways to do so. So that's kind of what's important. And so let's look at, so I want to emphasize that we have this crystal structure that's showing us that the water is coordinated. So that's why we call it a hydrate. And so it's really binding these 4 ones more strongly. But again, we have this green color. And then it does mention, well, this is with the hexamine complex. Because then there's a variety of ways to what's called dry them. And they don't always involve just like straight heating. So sometimes, so for example, to prepare like the nickel chloride compound, you would want to what's called reflux it in toluene. And if you refluxed it in toluene for long enough, eventually the water would be driven off and you get the anhydrous. And this is a good piece of equipment. I generally talk about it in different contexts. And this would be one, so usually I talk about it in this context, but this would be another reaction where Dean Stark would be useful. And so again, basically you could have your hydrated nickel chloride compound in here with toluene, you reflux it for a few days, and then this Dean Stark apparatus, what it does is, right, you have your solvent kind of building up over here, and you have to be somewhat intelligent when you pick your solvent because it has to have a lower density than water. So you can't use, for example, dichloromethane. So that would be more dense, and then you can't drain out your water. But as long as water is more dense, it's on the bottom, you can drain it out, and that keeps driving your reaction forward. So again, we just want to take away that it is complex to our metal when we find it like such. And so again, these are just different examples. We're not going over how to purify them. Some of them, like I said, can be liberated by heating. Others need more purification. All right, so single replacement reactions. So there's a ton of these. And what drives them forward? So can you, do you know what drives them forward? There's a hint in the handouts that I printed. What drives our reaction forward? Let's look at a few things. So let's try, oh, how did it know that I wanted to do these 2 demos? All right, so let's do one that you did in lab, if I can find it. And so I'm just going to do, so our single replacement reactions, right, what's happening is, so let's look at several ways to describe them. So we can call it a redox reaction. And redox is technically short for oxidation, reduction, but all we're saying is electrons are being exchanged. And then so fundamentally, a single replacement reaction, if we look at what's going on, we have some metal here, and again, we're going to redo one of the ones you've done in lab to emphasize this. So, right, you did copper sulfate in lab. I picked copper chloride just because it was the one I saw. Right, the counter ion doesn't matter so much in this case. So, right, the counter ion, to start thinking like a chemist, right, it really just dictates kind of solubility. And so I'll write down what we're doing on our demo. But it's essentially this one on bottom. And we did this in class, right? So you took copper, really it's copper 2+. I'm using copper chloride. And then we're going to add zinc to it. Again, like I said, we did this in lab. but just good to kind of recap. And so now I'm just going to stick my zinc in there. So good sign turning black right away. So let me pull up my demo cam. So right, it's starting to react. Let's do another one. Let me label these. So, copper, zinc. And so kind of a fun fact. I don't know if y'all are into what I'll call modern mining, right? Like you can go to estate sales and whatnot and then try to get out silver and gold. And so how they do that, I can never find, here's my silver nitrate. So I have silver nitrate here. I'm just putting some silver in. Bloop, 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 bloop. And so you can retrieve out the silver by putting in some copper. So let's watch that. But what is dictating this? So what reference sheet did I give you? Kind of what's driving this? What should you reference? Yeah, so the activity series of metals, right? So make sure you grab one of the activity series. And I gave two different versions because I had different feelings about them.
What does that mean?
I mean, they both say the same thing, but in different ways. Sorry, let me get over there. I've trapped myself. Ugh. All right, so what we're getting at is, well, how do we know if a metal is going to be replaced or not? So I would grab both of these, because like I said, they say the same thing, but then one of them has extras. All right, so if you look at this one, so it doesn't matter which one. So they both have the same activity series. But the rule is that the metal can only knock out anything that is below it, right? So if we're looking at our activity series here, and I'm just comparing, let me see if I can find a virtual one. For some reason, if you Google them, you don't get the same stuff. Here's a similar but different one. And so, okay, the reactions that we're looking at, so we did zinc is trying to kick out copper. And we see that zinc is above copper. So yes, zinc is capable of kicking out copper. But right, if we were to do the reverse reaction, so if you had, for instance, some sort of zinc anion, so right, zinc sulfate, and you try to add copper to it, well, you would get no reaction, right? And so part of this has to deal with like reduction potentials and blah, blah, blah. We're not there yet. We're just appreciating the activity series. So again, right, since copper is below zinc, it can't kick it out. All right, so that's the problem with that one. And so now looking at our reactions though. So we, like I said, we set up this one. And this one is going nicely. So we're making zinc chloride in solution and putting out our copper. So I'm going to swap. Where'd it go? Right, so there's our nice copper. So that's coming out of solution. Sorry, let me pull up our document cam. So right, we can see our solution's fading. So that's kind of cool. So there's our copper. And then I wanted to point out, and this one's just pretty now. So check that out. So we're getting nice silver crystals coming out of solution with the other one, right? And then we should be slowly making copper which you can tell right by the coloration. So let's look at that other reaction. And so my point and what I was getting at is this is the common technique that people use to mine out, again, if we're talking about kind of our modern mining and what people do now to get silver and other metals out of jewelry is, right, eventually you make some sort of silver solution. And again, right, the whole point of the counter ion is that you're just trying to dictate the solubility or not. Which is why I also gave you this one, because it has the activity series, but also tells you solubility, right? So I don't care so much about it being silver nitrate, but the reason why it's nitrate is, so if we look at nitrate, right, what are exceptions that are solid? Are there any insoluble nitrate compounds? No, right? So that's why you get a lot of nitrates in the stockroom, since, okay, silver nitrate is soluble. That's what this little AQ is also telling us, right? So this is soluble. And you could also think about what other appropriate reagents, so, right, like silver acetate could have also worked, just as an example. That would probably be the only substitution I would do. You want to stay away from perchlorates because those could eventually be explosive potentially. But right, you can swap out the anion. Yeah.
These two sheets have the list a little different.
Is there like a discrepancy on the metal?
Yeah, like calcium is above sodium on this one, but swapped on this one. And also like mercury and silver swapped.
Yeah, I wouldn't worry about like minor discrepancies like that. So again, that has to do with like the redox potential, but we're not talking about that today. But yeah, we'll eventually do a lab on this, but yeah, so there's a few small discrepancies. And again, like we're seeing this reaction take place right here. So again, we added our copper metal, right, dropped it into our silver nitrate solution. And then we're seeing it become more blue as it makes copper nitrate in solution. And then, right, we kick out that silver. So that's looking nice and pretty there. Pull up the cam. All right, so again, right, you want to think like a chemist. So we're always thinking about our counter ion. And let's see, here we go. So I was looking for other displacement reactions. And so why I gave you the other sheet is because you need the reactivity of these halogens down here. So again, right, fluorine can replace everything below it. And so again, these are just examples of reactions. So we have our bromine reacting with sodium iodide, and our bromine can kick out the iodine since again it's lowest. That's also why iodine is a regulated substance. So I think I've hinted at it, that it's used in the synthesis of meth, but again, like that's synthesizing meth is super trivial, so that's why it's like not that exciting. But that being said, right, iodine is regulated since anything can kick out iodine, so it makes a good group. It makes a good leaving group, so that's why it's popular in synthesis. But now it's a regulated substance, so thank you, meth. So again, right, activity of halogens, so as long as it's higher, it can replace it. All right, so now let's look at our double displacement reactions. And so I'm going to do, I'm going to do this one. And so let's look at this reaction. Again, right, we want to kind of refine our understanding and put everything together. So I'm adding sodium chloride. Again, like it suggests in our reaction, it's aqueous, meaning it's in solution. Oops, and let me, sorry, pull up my cam view again. And so again, we're just showing, yes, it's soluble. We can verify that with our solubility rules. Yes, sodium chloride is soluble. And then we're going to add silver nitrate to it, which we had already established, right, that the nitrates are all soluble. But let's watch closely and see what happens. All right, so what happened there? What's the white stuff? So precipitate, and then...
Is it silver chloride?
Yes, and then so this does give it away, right? But we need to think about, well, what are our two possible products, right? So then just do the double displacement, so meaning you swap your anions, right? So you can see that the general formula is AB plus CD, and then we pair A with D and C with B, right? But then the question is, what is truly driving this reaction forward, right? Because otherwise, if they're all insoluble, you're just going to have solutions kind of staring at each other. So water formation does drive it, but that would be with a different type. So let's add that, though. So neutralization reactions are also double displacements. All right, we could call this an acid-base reaction. And so just fundamentally, right, we have HCl plus NaOH. I'm just picking a super simplified one. Do the double displacement, so then we pair HOH, which is water, like you mentioned. So yes, right, the formation of water can drive the reaction forward, especially in a neutralization.
So it's not because they're aqueous though, like they're...
No, so in this case, right, so being aqueous just means that they're like chilling together. I don't know if I have, I'm trying to think. Well, I could mix two things together. Yeah, we'll go there. But we still haven't answered, so what drives it forward? So we answered what the precipitate was, right? But it's really this formation that's driving it forward, right? So when it's a solid, it's dropping out of solution. So then if we're thinking of our equilibrium, right, this is essentially dropping out and then driving this reaction forward to completion, right? So then you get all these beautiful solids there. So there's your silver chloride precipitate. And so again, right, how do we figure out what our products are? So once we do the double displacement, these are our two kind of possibilities, right? And then you want to check the solubility rules. So you can look up sodium nitrate, but we established, right, that all nitrates are soluble. So then this has a little AQ, right, meaning that it's still in solution. And so, right, it really just means that they're floating around separately. So they're just floating around separately. But then, right, what we're saying, when the silver and the chloride meet, they actually drop out. And again, right, we look at our rules. So we find our halide ions. And then it says, oh, there are exceptions, right, when you have silver, mercury, or lead, that those will form a precipitate. So yeah, that's exactly what we're seeing here. But then, you know, just to maybe drive home this point here. So right, let's just do another reaction. And so now I'm going to add. So let's have a sodium phosphate here. So sodium phosphate, and then let's react it. Sorry, I'm thinking about what I want to react it with. Let's do, I was looking for this guy. No, not this guy. Yeah, let's do potassium thiocyanate. Right? Drop that in. Nothing happens. And so, right, why was there no reaction? think about what was in solution, right? There's nothing to happen. So we can, you know, we have to picture them in solution. So, right, they're aqueous. So we have sodium floating around, phosphate floating around, potassium, thiocyanate. But when they meet, right, this is still soluble. So you're basically asking, right, so our potential products are sodium thiocyanate, but this is still soluble. And then our other one would be potassium phosphate, but this is also soluble. So because all our potential products are still soluble, there's formally, right, no reaction is what we observe then. So that kind of makes sense then. So we have to have something driving the reaction forward. Again, a formation of precipitate. Let me label this real quick. So yeah, let's try another one just for fun. Oh. Someone's going to kill me later for this. Making a disaster.
She spilled salt.
No, it's not that. It's like all the little metals that I'm like, oh, these are heavy metal waste now. All right. Oh, other things. Let's do another one. Other things that can drive our reaction forward are complexation. Go. So this is iron 3. Might need acid. Let's see how this goes. And sorry, I keep losing my chemicals. So let's see what happens. Boom. So nice blood red compound. And so this is driven by complexation. So we'll do that reaction, I think, at some point in lab. But all that happened there, so we had FeCl3, and then we added, oops, come on, plus potassium thiocyanate. And so this forms this iron 2 complex, or iron thiocyanate, and it's coordinated. And so this is red, and so this can be, again, another type of reaction where we have our coordination, and right, gives off KCl. So I'll say metal coordinating. And so, right, this is a little bit not so obvious, right, because this doesn't have to deal with solubility, but rather the metal adding something. And usually our big hint, though, is color change. And so, right, that was pretty distinct there. Again, going from our pale orangish iron chloride to then that. And I am curious, because you can push around iron compounds if I added some base to it. But. And then again, our solubility rules is what drives this forward. So we're trying to see if we have an insoluble compound as our product there. And so this is just another set of rules, but I think all the ones you have should be similar. And then just trying to finish the rest of the chapter. So like we mentioned, our acid-base reaction is a double displacement. And then, like we mentioned, we have our redox reactions. So I think we'll probably have to save this for next week, kind of getting into how to assign oxidation states and all that. But again, we'll kind of go in the different types of reactions that are oxidation reduction. So we'll get into it, but generally we'll find that like a combination reaction and single replacements, those tend to be our redox reactions. But like I said, we'll get into that and how to figure out oxidation states probably next week. Any burning questions or anything?
Is it only for single replacements, not doubles?
No, so double generally, right, keeps your oxidation state. So that's a good question. So, right, before you dash out of there, take that in. So again, right, your double displacement, we actually want to say this is not redox. So generally they are not redox reactions since they're just, right, swapping partners. So generally their oxidation state is not changing. So again, in general, right, they are not redox reactions, but is instead the precipitation that drives it. So precipitation, or like we mentioned, right, the water. So both of those are what drive that reaction forward, as opposed to oxidation states. All right, other good burning questions? So again, if you need to make up stuff, you can just like follow me to the lab or something. We'll migrate over there and get stuff going. Otherwise, you're free to go, and I'll see y'all next week. Yeah.
Thank you.
Thank you. Oh, and I will end this stream. Thank you.